So good evening in India and good morning in Calgary. So this is this IMSC Diamond Jubilee Distinguished Lecture Series. So today we have with us Professor Barry Sanders. Uh, so Professor Sanders is the director of. He is a very well-known figure in the field of quantum information computation and quantum optics. So he is a director of the Institute of Quantum Science and Technology at the University of Calgary, Canada. And he is also the lead investigator of Alberta Major Innovation Fund project on quantum technologies. He is a distinguished chair professor at the University of Science and Technology in China and also a Vajra visiting faculty member at Raman Research Institute, India. So Professor Sanders received his bachelor's degree from the University of Calgary in 1984 and a diploma of the Imperial College, which was supervised by Professor Thomas Kibble, and in 1985, and then he completed his PhD in Imperial College under the supervision of Professor Peter Knight. And he pursued his postdoctoral research in different universities like an Australian National University, University of Queensland, and the University of Waikato. And so thereafter, he joined as a faculty member in the Macquarie University in 1991, and he was there as a faculty member till 2003 when he joined University of Calgary as a faculty. So Professor Sanders is particularly well known for his seminal contributions in theories of quantum limited measurement, so highly non-classical light, and then practical quantum cryptography, optical implementations of quantum information task, etc. So his current research interests include quantum algorithm and implementation of quantum information processing task. So Professor Sanders is a fellow of the Institute of Physics in United Kingdom, the Optical Society of America. He's a fellow of that. He's a fellow of Australian Institute of Physics, the American Physical Society, and the Royal Society of Canada. And he's also a senior fellow of the Canadian Institute of Advanced Research. He is a former president of the Australian Optical Society, former founding co-chair of Canadian Association of Physicists Division of Atomic, Molecular, and Optical Physics. Is a former leader of Optical Society of American Quantum Optical Science and Technology Technical Group, and so he has been awarded the Doctor of Science degree of Imperial College in 2016. So Professor Sanders is, he's involved in, highly reputed journals in editorial activities. Like he was editor-in-chief of New Journal of Physics from 2015 to 2020. He was a former associate editor of Physical DBA, former editor of Optics Communication, and a former editor of Mathematical Structures of Computer Science. So, so today, Professor Sanders is going to talk about this the observing a challenge in Hilbert-space inner product. So basically, so this is something I guess related to this non-Hermitian quantum mechanics and its further developments. So without further ado, I request Professor Sanders to start his colloquy.
Thank you very much, Shivashish. So you can see me, hear me, and see my slides, correct?
Yeah.
Okay, great. So thanks for the kind introduction, and I'm honored to be able to speak at this auspicious event. The topic is in the title. It's observing a changing Hilbert-space inner product. You can see the details in paper that was published in Physical Review Research this year. I will tell you a bit more than is in that paper. So there's other work we've done since, and we have an experimental collaboration I'll mention a little bit about. This work is done by me with my PhD student, Shalini Karavati, and postdoc Abhijit Alais, who at this moment are on their way to Australia, where they're They're both taking up positions in Sydney. Okay. And I guess before I go to the next slide, I'll just give you the idea of what I'll be telling you about. So we learn in quantum mechanics that all physical states can be represented by vectors or rays in Hilbert space. The norm of the state doesn't matter. And the question that I was asking that led to this project is along the following lines. It's, is the Hilbert space inner product unique? Does it have to be unique? And what would happen if you go to sleep at night with one inner product and you wake up in the morning and the Hilbert space inner product would be changed? Would that be observable? And this is against a background of Hilbert space. The choice of Hilbert space inner product is known not to be physical. But if it changes, then it wasn't known whether it would be physical or not. And as Shibashi said in the introduction, this does tie in with the whole PT-symmetric quantum mechanics as well. Okay, so this on the left, you can see the 5 topics we'll cover. It's just an introduction to the field. I'll give some background. I'll tell you our approach to it, tell you our results, and come to conclusions. On the right, you can see a picture of Calgary. We're close to the Rocky Mountains. And so this is where I am right now as I talk to you in that city. And below, you can see lots of ways to reach me on the internet, social media, and other ways. Okay, so let's just talk a bit about inner product quantum mechanics. And this is basic knowledge when we do quantum mechanics, undergraduate level stuff. On the other hand, if you're like I am, I learned it, I just took things for granted and didn't think about it too much when I first learned it. So I'll go through the basic details here carefully so that we understand the basics and then we can start manipulating those rules. So first of all, Hilbert space is used to describe physical states and measurements in quantum mechanics. What is Hilbert space? Well, Hilbert space is a complete inner product space, and it's complex valued. So let's think of Hilbert space as a pair. There's a vector space, and for the vector space, you can think of all the kets, right? So this is ket psi. So just think of all the kets as the set of vectors. And then we have an inner product, and the inner product maps a pair of vectors or a pair of kets to a complex number. And the way that we do this is if we're given 2 vectors, ket phi and ket psi, then the inner product is the overlap between the 2. But something really important happened here. And in order to understand the overlap, we turned a ket into a bra. And this goes back to Dirac's language. The inner product to him was the bra ket. And he used the term bra ket as a bracket. So that this bracket represents the inner product. And we have rules for turning a ket to a bra. If the ket is a vector, complex valued vector, the bra is the row vector and complex conjugate of the elements. And then we just have a dot product in the sense of how we think of dot products over complex space. We can do it with functions as well, psi of x, like in Schrodinger's equation. And then we make a psi star of x, but we also include an integral. So we have rules for turning kets to bras. And this is what I want to play with. I want to say that suppose the rule changes overnight, what would happen? Or it changes, I think I'll put it this way, that you wake up in the morning with one inner product, you go to sleep, it's another inner product, and by the time you wake up the next morning, it's snapped back to the original. So this is the question that we're asking. And then we can start associating kets and bras with physics. We can think of kets as being states. And in operational quantum mechanics, a state is a description of how you prepare the system. And we can think of the bra as being a description of the measurement. So if ket psi is an electron in the spin up state, so I tell you electron and spin up, then we're presuming that we have a common language to discuss it, that the electrons can come from cathode rays. We can then have a magnetic field and lift the energy degeneracy of the spins so that it will relax to a spin up state. So when I say electrons spin up, it presupposes we have a whole language for what that means, and what it means is built in the preparation. And so a ket is a ket with the label psi is really just an encoding of a common understanding of how to prepare the system that way. And then if you accept what I say, it's always interesting. You know, we will say prepare a state, but it becomes redundant because a state is a description of preparation. Then the bra phi, the description of measurement, would be how do we measure that the electron is spin up? And we might have a common language where we agree that we have a single electron transistor and a reservoir, and that the electron will only tunnel through the single electron transistor if it's spin up, and that will result in some current that will lead to a register of a measurement. So if I say measure the state, measure the spin of the electron, it can have all that language built in. It's a description of the measurement. And then the overlap is given by a complex probability amplitude. But essentially, we use the Born interpretation. We do a mod square, and the mod square tells us the probability given preparation psi, positive outcome of the measurement of phi. So that's a lot. You know, the inner product is something we take for granted, but I want to make sure that you understand mathematically and physically what it means. And until our work, the question of whether and how the change of an inner product would be physically observable hadn't been touched. So that's the new thing here. And our aim is to establish a framework that's consistent with quantum mechanics. And this framework deals with changing Hilbert-space inner product between preparation and measurement. So the inner product can change spatially. You can, you know, prepare an electron in one place, the electron spin in one place, and then it flies to another place that's measured. It could be inner product changing over space, or it can change over time, wake up in the morning with one inner product, go to sleep, and it changed. And we want to make sure that we establish that framework. And it's a loaded issue when I say it's consistent with quantum mechanics, because we're building in our prejudice that we believe, so Shalini, Abhijit, and I believe that changing inner product is consistent with quantum mechanics. And that's important because as I get to PT-symmetric quantum mechanics, whether it's consistent, there's a debate, and I'm going to argue it's just quantum mechanics. Okay, so why is it important to deal with it? Well, first of all, it's important to deal with this question because it's allowed to, that there's nothing in quantum mechanics that says the Hilbert-space inner product can't change. And so on a foundational level, we should know what happens. But also we should know about it because there's work that deals with different inner products. And so different works have considered what if the inner product were different? Not that it changes over time and space, but would quantum mechanics be different with a different inner product? And this is answered. You can see one points to the bottom of the slide. Now I'm using the DOI, the digital object identifier. The DOIs are long, but the DOI service offers a hash. Well, there's a hash service. Shortdoi.org does this. And so when I do this, if you just put 10/ and then up to 6 alphanumeric characters into doi.org, it'll come up. So it's just a shorthand way of referring to the paper. So there were works by Scholz, Geyer, and Hane, and also later by Mostafazadeh, and they point out mathematically that they discuss the issue of different inner products and show that they're physically equivalent. But not the case of changing inner product over time or over space.
May I ask a clarifying question here?
Sure.
Yeah. So is it not possible to keep the result same by changing the inner product and changing the bra at the same time?
Yes.
So is it that the point that so for given any psi, we have a corresponding bra state? So if you change that identification and change the inner product, maybe the formula for the observable will change, but the result will remain the same.
Yeah, I'll get into all this very carefully mathematically. But when you say that for ket psi there exists a bra phi as a dual, that's not always true. That in quantum mechanics, it's not consistent to have a ket for position and a bra for position. That's what leads to the Dirac delta, and that's not consistent with the mathematics of the inner product. So we have to be very careful with these points. But if you give me a bit of time, I'll get to the issue.
Right. Okay. Thanks.
Okay. Thanks. Yeah. Just give me some time. I'm telling the story, and then I'll get to the mathematics carefully. But your question, I'll fully answer. So is it advantageous to change the inner product? Well, there are studies. Reference 2 is actually work that I collaborated on. It's experimental work. It's by the group of Peng Shui at the Computational Center in Beijing. And we deal with the quantum cloning, and effectively we find that changing the inner product is equivalent to non-deterministic perfect cloning, which there's 2 areas of quantum cloning out there. And then also there's the question of faster than Hermitian quantum mechanics. So there's speculation in work by Bender, Brody, Jones, Meister in the 3rd reference, and they say they don't prove it, but they ask the question of whether a different inner product could lead to a speed up for computation based on breaking the speed limits that are inherent in quantum mechanics, but not rigorously formulated. Okay, and then the other motivation that I have for doing this work is observing exact PT-symmetry. And so we know from Brody's work in reference 4 that if we have quantum mechanics for a closed system, then a different inner product won't result in any change. And so your question about whether it's equivalent, so yes, in a closed system, it's known that a different inner product would not be any different from quantum mechanics. I think for the reasons you say, and if you restrict the finite dimension where every ket has a corresponding bra, then it becomes clear, but still not clear about changing it over time. And also the idea of an open system. And the open system, as I'll show you, is related to the question of changing inner product. So essentially the question was unresolved mathematically. Okay, so what I'm going to claim here, and I haven't gotten the details yet, I'm still doing the storytelling. First of all, I'll show you that we have a framework that's consistent for quantum mechanics, consistent with quantum mechanics for changing the Hilbert-space inner product, that changing inner product is equivalent to being an expression for a quantum operation, which is a completely positive map on operators on Hilbert-space, that we show what this framework explains PT-symmetric quantum mechanics and is in fact equivalent to it. And then I'll discuss a unitary qutrit protocol for simulating the IP change of a qubit. And it turns out that in order to deal with the changing inner product, we open the system, but based on a Stein-Sprang dilation argument, you would say that an open system requires the cube of the dimension of Hilbert-space. We only need 1 extra dimension of Hilbert-space. So we can show that our simulating inner product change in our universe, if the inner product doesn't change, but we want to simulate it, we need an open system, but we only need 1 extra Hilbert-space dimension to do it. And the novelty of our work, first of all, is we bring C-star algebra in to formalize and operationalize the changing inner product. And normally in quantum mechanics, we try to, most certainly in theoretical physics, we try to avoid the C-star algebra because it seems to be an extra layer of formalism we don't need. But here we need it because we have to get to the purely algebraic level, make sure we have our rules clear, and then bring Hilbert-space in after, not start with Hilbert-space. We employ the freedom in Hilbert-space, this inner product, to construct this quantum operation. The freedom in Hilbert-space representation is really basis changes. So we still accept the rule that a change of basis doesn't change the physics. And then finally, we operationalize PT-symmetry itself via an inner product change. So we claim that the interesting questions in PT-symmetry are inherent in our framework. This is the background. I mentioned some of the paper. I mentioned all the papers here. So in the upper left, you can see a 24-year-old paper by Bender and Bottcher. And this is the paper that really launched the torrent of work on PT-symmetry. And they say in their paper, that Physical Review Letters article, real spectra in non-Hermitian Hamiltonians have PT. Okay. Was there a question? I heard somebody's voice. Sorry, whoever's speaking, you're breaking up. Try again.
Hello?
Can you hear me? Shivashish, can you hear me?
Yeah, I can hear you. I can hear you.
Yeah, somebody's speaking, but the voice is not coming
voice
across.
Is breaking. Yes, yes. So maybe Arindam, you can ask question later if okay.
Okay, I'll keep going. So the real spectra and non-Hermitian Hamiltonians having PT-symmetry, they point out, first of all, they introduce the PT-symmetry. In particle physics, PT is parity time. But they say, they point out that you don't need parity in time, you just have a linear and an anti-linear operation. So they just say, if you ask whether a Hamiltonian can be physical, if it's non-Hermitian, they say that if it has a real spectrum, then it has PT-symmetry. And this is what opened the field of PT-symmetric quantum mechanics. Mostafazadeh, 5 years later, proved that if you have exact PT-symmetry, which is tied to the closed system, it's equivalent to hermiticity. So Mostafazadeh is essentially contradicting what Bender and Bottcher write. They're saying we modify quantum mechanics by having a non-Hermitian Hamiltonian, and Mostafazadeh is saying, actually, if you have exact PT-symmetry, you have Hermitian Hamiltonians, and then inherent in his work is a change of inner product, that what you call Hermitian depends on your choice of inner product. In the upper right, you can see Brody's paper on the consistency of PT-symmetric quantum mechanics. So he's saying that if you choose a different PT-symmetry and hence a different inner product, you get the same quantum mechanics. And then down below is a paper a couple of years ago from Peng Shui's group, and I'm one of the authors. And that's the one where we just say, if you have this pseudo-unitary, which is related to PT-symmetry, and you impose the rule, then cloning in a PT-symmetric universe is equivalent to non-deterministic perfect cloning in a simulation. Okay, so that's the context. Now I'll go to the mathematical level, and I'm just going to define the things to make sure they're absolutely clear. First of all, what do we mean by PT? It's motivated by parity time in particle physics, but not that. P is a linear isometry on Hilbert space. So an isometry is a mapping that preserves inner product on an inner product space. And T is antilinear. And antilinear just says the map of a superposition of kets is the mapping of each ket, but we complex conjugate the coefficient. So that's what the antilinearity does. If we require that they square to identity and that they commute. So that's the definition of P and T. It's consistent with particle physics, but broader. Then we can define the PT-symmetric Hamiltonian by saying that the Hamiltonian is PT-symmetric if it commutes with PT, but it's not required to be Hermitian or self-adjoint at all. And then we talk about exact PT-symmetry. And exact PT-symmetry is not just that they commute, but that they share all eigenvectors, and hence all that requirement that all eigenvectors are shared between the Hamiltonian and PT guarantees that the eigenvalues are real. And some of you might be surprised, because if it commutes, you'd say they already share all eigenvectors, and that's not the case because T is antilinear. So sharing all eigenvectors is a stronger restriction than saying they commute. And all eigenvalues are real then ties back to what Bender and Bottcher wrote about in 1998 about the real spectrum for the Hamiltonian. So that's exact PT-symmetry. The experiments on PT symmetry don't.
Now I'm audible. Hello.
Sorry,
Now I'm audible clearly.
I hear you. Yeah.
Yeah, I'm saying that are you restricting yourself to the inner products for which, I mean, if you take the inner product of two positive matrices, the answer will come positive. Are you restricting yourself to those kind of inner products?
No, because we're on complex space, so the inner product is complex valued. So positivity is not well defined.
Okay.
The overlap between two quantum states is a complex number.
Oh, so you are okay. So you are considering the inner product in the projective Hilbert-space, not the LH. LH means the
Right.
bounded linear operators.
So I couldn't make out all the words you said. Try again.
Yeah, I'm saying that means you are defining inner product here to the projective Hilbert-space, right? Means not the not in the LH, not where the density matrix sits.
No, there's no density matrix yet. I'm
Okay.
going to approach it from a C-star algebra approach. So I'll talk about everything algebraically, whereas the density matrix already, density matrices are operators, so homomorphisms on Hilbert space. Then we have to get to the representation at matrices. So there's no matrices and no operators yet. I mean, there's operators here, but in an algebraic sense. I'm not yet getting to the matrix level.
At the end of the talk, I will ask some questions.
Sure. Okay. Thank you. So now that third block, I've been clear about this eigenvalues being real. And then the last one is the exact PT symmetry, and then the knowledge that exact PT symmetry is equivalent to quasi-hermeticity. This goes back to most of Azadeh. If we work on that for a finite dimensional Hilbert space, and in that case, then I introduce M, which is a bounded bounded operator. It's bounded operator on Hilbert space. Finite dimension is automatic. Then we can say that this is most of Azadeh's proof, essentially. For all finite dimensional diagonalizable exact PT-symmetric Hamiltonian, so H subscript PT, there exists what's called a metric operator, eta. Eta is self-adjoint. Eta equals eta dagger. The dagger is defined with respect to the given inner product. So you tell me an inner product, it can be any one. Then eta dagger is conjugate. Then the Hamiltonian can be regarded as Hermitian if we don't, instead of requiring that the dagger of the Hamiltonian equals itself, we require that the conjugation of the dagger of the Hamiltonian by eta is equal to itself. And so this is what most of Azadeh did to prove the equivalence between PT symmetry and the inner product. So we generalize the inner product definition by including conjugation by a metric operator. And then we have the rules. So in the next line with the Hermitian conjugate, I'm just showing you that we're using the dagger and we're using symbolism that's consistent with standard notation in quantum mechanics. So there's M of ket psi is ket M psi, and the overlap is given as follows, where we have M dagger on the left. Okay, so now you can see with that conjugation by the metric operator, the Hamiltonian doesn't look Hermitian in the usual sense, but if there exists a positive self-adjoint operator, eta, then it works. Okay, so that's most of Azadeh's proof in 3 lines. Okay, next. So the key point here, and so I'm going to be very careful in this slide, is to tell you what it means to the adjoint. And the two people asking questions, have been keen to find out what is this, how we get the bra from the ket. And I've been emphasizing, and I hope it's really clear, that we're getting the rules without matrices, without column vectors and all that stuff. We're getting it algebraically. So in that case, we talk about the C-star algebra, and the C-star algebra is just the algebra of observables. So if you don't know C-star algebra, it doesn't matter because you use it even if you don't use the term. The algebra is just the algebra of observables, and the star operation in physics will write dagger for the adjoint, and mathematics will write the star. And because we have 3 different frameworks for doing a dual in this presentation, I'll use the star for the algebraic dual, turning a ket to a bra, if you like. I'll use dagger for the adjoint under the existing inner product, and I'll use a double dagger for conjugation for dual under the new inner product. And then we have the observables, then we have to have states. Now, we heard earlier a question about state being a density matrix, but strictly speaking in quantum mechanics, states are linear functionals. So given an observable A star A, that guarantees self-adjoint, then omega is the state, then the state acting on the observable has to be a real number, it has to be greater or equal to 0. And the other rule, which I'm going to break, so if you look in a book on mathematical physics for quantum mechanics, it will say the state evaluated on an identity matrix. So to a physicist, that could be an infinitely hot state where every energy level is equally likely, is equal to 1, and I'm going to break the rule. So I'm going to say that the state evaluated on an identity can be less than 1. And this is in red. So the red less than or equal to tells you that we're modifying a rule, and you can use your own judgment as to whether it's valid to tweak this rule, but I'll justify that it's consistent. Now, in order to go from observables to states, if we introduce Hilbert-space, so that, even in the question about matrix, so you can even ask the question, how do we even make this matrix? How do we turn kets to bras? And mathematically, this is all built into the GNS construction, the Gelfand-Neymark-Siegel construction. And this is the mathematical rule for turning kets to bras. And so we have our elements of the algebra. So just to make things simple, let's say you think of the Pauli operators, the sigma x, sigma y, sigma z, and you say, I've got my Pauli operators, the algebra form. Now I'm going to make Pauli matrices. First thing is that when you have a spin, you have a spin system, the size of the matrix can be arbitrarily large, can't be arbitrarily small. 2 by 2 is the smallest that's faithful. So it's not even unique. But we decide to make 2 by 2 matrices, then we would introduce a 2-dimensional Hilbert space, then we would make bounded operators in the Hilbert space, and then we would construct a matrix representation. I won't go into all this because I'll run out of time, but essentially we have our set of rules. Pi is what creates that representation. And then the observables connect with states. This is the ket to bra, goes under a mapping. And we didn't find a mapping symbol in the literature, but the sharp symbol is known as a pullback in mathematical physics. So I put that in red because I'm using a known mathematical symbol, but I'm using it in this context the first time. And so sharp pi gives us the representation of operators, of the algebraic elements as bounded operators in Hilbert space, and the sharp pi pulls it, essentially turns the ket to a bra. And then it has certain properties that have to be satisfied. And here I'm saying the representation of the adjoint of the operator, star because it's the algebra level, is the adjoint of the representation of the operator. So this is the conjugate. Now this could be, it can have that metric operator. So it just has to be consistent. And then we can think of sharp pi and the density matrix rho that came up in a question. So if you talk about a density operator rho, then sharp pi acting on rho is equal to omega. So the connection between the state in a strict mathematical sense and a density operator is related by this pullback, this sharp pi. And then if we think of a pure omega, then we can just talk about a projection operator under the pullback, and this would be for a ket psi. So using this pure state argument, we're able to connect bounded operators to Hilbert space itself. And then the idea of the proof, this goes to Brody's work, and I think this is in the essence of the questions that are coming up, is that the different representations. So if we, so Brody's paper I've put into one line proof. And we're just saying that if we take a state mapping an operator to trace So in this representation, trace gives us that inner product, trace of rho pi of A, and we change the operator A. So we get a different representation. This is under a different inner product and a different row, we get the same answer. So basically it says that, if you change your ket, you change your bra equivalently, and you can't see any difference. The question that I've asked here is what happens if you wake up in the morning with one inner product and you prepare the state, and by the time you go to sleep and measure, the inner product has changed. So the question here is what happens if the change of inner product, if there's one inner product at play when you prepare and another inner product when you measure. So that's the point. Okay, now we'll run out of time. So I'll just tell you the essence of the slide, but not go through line by line. But so what I'll tell you here is we're now going to allow the inner product to change. So this calligraphic I is inner product. Eta is the metric operator. So I'm going to label the inner product by the metric operator. So eta is now a metric operator, and it's also a label for the inner product that's represented by that eta. And so the Hilbert space here maps to a new Hilbert space. We keep the vector the same, so the kets don't change at all, but the inner product has changed. So how you create a bra from a ket has changed from morning to night. And the new inner product is then given by this rule. And so I won't show the consistency, but it's consistent. If you have ket phi and ket psi, the overlap is no longer turn the phi into bra, but it's turn the phi into bra and multiply psi by eta. And then equals colon means defined. So the right term is defined by the left. Then changing the inner product by inserting a metric operator, I will then use eta also as a label here in the subscript. And then we do that. This block is showing you mathematically that introducing a change of inner product in this way is consistent with all the mathematical axioms of representation. So basically we're saying that, the usual ways of creating matrices out of operators are all consistent. And I'll skip going through that, but it's there if there are questions later. Then in order to check all the consistency of this, so this slide is all about making sure that our rules are consistent with every rule of quantum mechanics, except this, except that a state maps an identity to identity. So it's subunit. I've changed a property of mathematical physics. I've generalized it, and that means that we have to check everything carefully. We can't just break a rule and claim it's okay. And so up over here, this is a category theory diagram. It helps you visualize what's going on. And so S is state space. On the left is the old inner product. On the right is the new inner product. So S maps to S is how states change. B of H to B of H eta is how operators change. And H to H eta is how Hilbert space changes. So Hilbert space changes under a change of inner product labeled by eta. The operators we prove are change according to a channel, quantum operation. So we prove that E sub eta is a completely positive map on Hilbert space. And the states change under a dual to the channel. And then the way that we prove it is we do our lift. The lift takes Hilbert space to B of H. So Hilbert space is spanned by kets. B of H is spanned by ket bras. And then S, we go through this pullback. We go through axiomatically what's required on every level, make sure it's consistent under inner product change. And so the story is then that the inner product change on Hilbert space creates a channel, I keep saying channel. It's not trace preserving, so that's why I can't say that. It's a quantum operation from B of H to B of H eta, and then there's a rule for states. And then I said to you about the freedom of Hilbert space. So there's two elements. One is a basis change that we regard as unphysical, and the other is a change of norm. And what's going on in the mathematics here is we're essentially saying that the channel is a composition of a norm change and a basis change, and all the physics is caught up in the norm change. And the norm change then manifests with operators. There's a conjugation, but instead of conjugating by eta, we wind up conjugating by square root of eta. So that, there's that rule. And then the idea of seeing inner product change is to see whether the we're seeing this change of norm, and the norm can be different for different eigenvectors. And then it's operational because it can be done by process tomography. So if we have a quantum operation, we could prepare stuff in the morning, measure in the evening, do enough different instances so we could do full process tomography. And that would tell us, by process tomography, that would reveal the signature of the inner product change. Okay. This diagram is just showing how to implement the exact PT-symmetric Hamiltonian dynamics. So it's the closed system exact case. And dynamically, we can ask the question, if the inner product changes from morning to night, how does the system evolve? Now, our work, we only strictly say, we study the morning, we study the night. We do not yet study how it changes during the day. This is future work. I had an undergraduate who did some work that made sure that we were able to break up a mapping into a sequence of maps on infinitesimals. So we got a few results that are helping me get confident about this. But essentially, the unitary evolution is given by the exponential of the Hamiltonian, assuming it's not time dependent. If it's time dependent, we have to do time ordered exponentials. And we change the inner product. So we just compute some eta compatible with inner product change. As I told you, the only physics that can be observed is the change of norm. And it turns out we'll introduce the term kappa, which is the inverse of the norm of the inverse of eta, which is the metric operator describing the change of inner product. And over here, once we construct our evolution operator, then we implement the state, maps to the state, conjugate it under U, but it has to build in that change of inner product here, because in order to make the row physical. And this UPT, this conjugation, is really the channel. And so here's what goes on is, if the inner product changes from morning to night, there's a channel. Then we can do things at the other end, like measure. And then if we then want to send it back, the channel has a change of norm. And what I said to you about the experiment I was involved with that published a couple of years ago, that quantum cloning becomes equivalent to non-deterministic perfect cloning. The non-deterministic aspect is built in this kappa. So the idea of inner product change is we do regular quantum mechanics, but we lose stuff. So it's an effective open system dynamic, but there's no open system. It's the change of inner product is causing stuff to get lost. So this kappa quantifies how much stuff we lose, and we have to lose things to preserve causality in quantum mechanics. And down here is another category theory type diagram to explain how mapping states and mapping operators is consistent, and these lifts between the two related to the GNS construction are built in. Okay, so I'm almost done, just this slide and then conclusions. And then I hope I leave it. I know there's questions, so I'm going to leave a lot of time for questions. So the qutrit simulation. Now what we're saying is, okay, unfortunately, we don't live in a universe where we think the inner product is changing. Can we simulate it? And I said at the beginning, we can simulate it by just adding one extra dimension of Hilbert space. So I'm going to show you with the qutrit. So let's say that you have a qubit, a two-level system, and the inner product changes from morning to night. How do we simulate it? Well, according to Stein-Spring dilation, which is a C-star algebra theorem, says that in general, the minimum number of extra dimensions you need is, well, basically, the minimum number of dimensions you need is cube. So if you want to simulate open system dynamics of a qubit, which is for a two-dimensional Hilbert space, you need 2 cubed or 8-dimensional Hilbert space. But we only need one extra dimension. So we don't need 8 dimensions to simulate this. We only need 3. So we take whatever state you tell me for the qubit, we embed it in a qutrit. And embedding means we just put 0. This is a 1 by 2 and a 2 by 1 vector, and this is 0. And then under the unitary evolution, our qubit evolves. There can be a change of basis. There can, but basically a rotation and a change of norm. And then the stars just say the qutrit can be whatever state we need. to make sure that it's consistent with the quantum mechanics with the usual inner product. And then at the end, we project. And so the idea is that we just embed a qubit into a qutrit such that the third level has no population, if you like. And then we allow it to evolve under the changing inner product, under that channel. And then we project back to the to the two-dimensional Hilbert space. And then down here, again, I won't go into all the mathematics, but we essentially deal with this mathematically. And what we're doing here, so we have a collaboration going on with the company Rigetti. Rigetti is a quantum computing company in California. And this is, what goes on with a lot of the superconducting quantum computing companies is their superconducting qubits aren't qubits, they're qudits. They have more levels. And so we're taking advantage of the fact that they have an extra level, and we're simulating with their qutrit. So that project is ongoing. And we essentially we set conditions for claiming success experimentally. So, in an experiment, you have to say, well, the experiment succeeds or fails based on passing some condition. And so we essentially come up with a cheating protocol that says, if somebody is lying to you that the inner product's changing, what power do they have? And we essentially come up with a condition that if we take the spectrum of the metric operator given by lambda 1, 2, then we pass the test as long as the distance between what we should get and what we actually get for the 2 by 2 matrix, it satisfies this particular bound, or satisfies that. So that's the experiment that we're doing. We kind of have a weak adversary model, but experimentally, qutrits are not that easy to deal with. It's kind of a very fast-growing field. Only in the past couple of years have there been serious experimental efforts studying manipulation of qutrits. Realizing them has been done optically with angular momentum states for years, but manipulating them is a very new topic and actually difficult experimentally. And then we use that Schatten 1-to-1 norm distance. That's described in this physical review letters by Jens Eisert's group. And we find that our extra dimension works well. And we can also prove that if we go to qudits, we only need one extra dimension. So if we want to simulate the changing inner product in a qudit, we just need a qudit with one extra dimension to be able to simulate. And I'll go to the conclusions. I'll say them quickly, and then I'm very happy to answer questions. First of all, we prove very carefully that inner product change is consistent with quantum mechanics, but we broke the rule that a state evaluated on an identity operator is identity. We made that less than or equal to. Prove consistency with mathematical physics. This, I don't think, was appreciated at all before, and we've made that rule very clear. We believe it's consistent, and I've given this talk to various mathematical physics groups, and nobody ever said it was wrong. So I'm getting more confident in that claim. Next, that inner product change is just a quantum operation, i.e. a completely positive map on operators on Hilbert space. Third, that all of this can explain PT-symmetric quantum mechanics in a proper mathematical framework. And finally, that we can simulate it by just adding an extra Hilbert space dimension. So thanks, and I'm very happy to take questions.
Okay, thank you, Barry, for this nice talk. Questions now?
Hello, can I ask? Hello, am I audible?
Yes, you are audible. Yeah.
Okay. Sir, can I request you to go to the slide number 8?
I'm there. Thank you.
Yeah. Sir, suppose you fixed eta, then this rule that eta to the power minus half pi a eta to the power half, is this rule unique? Means the transformation of the operators, will that be unique?
Sorry, you said 2 to the power of
No. I'm saying eta is telling you how to change your inner product, right?
Yeah, what we prove is that any change of inner product is equivalent to constructing a metric operator eta.
Yeah, no. So that is true, but how to change change this a or operator a? Is this transformation unique? Means you have to multiply it by eta to the power minus up. I mean, from both sides means eta to the power minus up and eta to the power half. Is this rule unique?
Okay. It's not. No, it's not unique. So
that's right. So that's not my first question. So this is not an unique.
No, but hang on.
Okay,
Wait. It's consistent. So we don't prove it's unique, but there's a lot of things to check to make sure it's consistent. It could be unique.
No, I feel that is not unique because this BH is isomorphic to D square dimensional Hilbert space, not the D dimensional Hilbert space. So this is a part of the question. I did not finish yet. Sir, please go to the slide number 9.
Okay.
Next slide. Yeah. Suppose you fix your eta, which is changing your inner product on the Hilbert space H, right? Now we know that this BH, the bounded linear of operators on the Hilbert space, it forms a sister algebra. So by definition, it actually forms a Banach space. So therefore, let's define the inner product on this BH as Hilbert-Smith inner product. Now, okay, so now if you are changing your inner product through this eta, this will lead to changing in the inner product on BH. And that will be a homomorphism if that the rule you said, if that is not unique, that will be a homomorphism. Okay, but to satisfy the quantum mechanical rule, I mean that thing, trace of rho A, that should be positive because that will give you the probabilities. And therefore, if you change the inner product on the BH using this eta, this will lead to a CPTP map on either on the I mean the first argument or on the second argument. So my question is that is this not intuitive that that changing inner product will lead to the quantum operation?
Well,
not TP map, CP map. Sorry.
Yeah. Okay, that's what I was going to say. Yeah. So you changed the CP map. So you said a lot of things, but you said, isn't it intuitive? And so I feel that the essence of your question is, it seems like you're agreeing. And first of all, yeah, I agree with your intuition on eta not being unique. That's fine. And then I guess what you're saying is this seems correct, and you're giving an alternative explanation that makes it intuitive. Is that what you're doing?
Yeah. So yeah, that's what I'm saying. That I mean, from the structure of this, I mean, whatever you are doing. So I feel that the way you are changing the inner product, so it will lead to, because what will happen? Suppose IN is changing the inner product from H to H eta, and then I mean, I'm saying that if you fix the eta, then in the BH in that Hilbert space, you can define new inner product, and that rule will be homeomorphic to that this rule I eta, and therefore, and I mean, and according to that rule, one thing has to be satisfied and consistent. One thing has to be consistent with the quantum mechanics, that if you multiply two positive metrics, means if you take the inner product of two positive metrics, it will give you always a positive number, because those are probabilities. Otherwise, it will not be consistent with the quantum mechanics. And therefore, if you change your inner product and still if you multiply, if you take the inner product of two positive metrics, it is giving you the positive number. Therefore, it is equivalent to a map on the BH, and that map has to be CP. Otherwise, this
sorry, just interrupt me for a moment. Just warning, like there's only 4 minutes left, so if there's going to be any other questions, we need to draw this to a close at some point.
Okay.
I mean, I'm agreeing with what you say. Like, I feel like you're eloquently stating what I've got. I think it could all be intuitive, but as I said early, I changed the rule here. So in order to establish it, to me, it's intuitive, but not everybody has all the mathematical physics training, you clearly have it, but we did have to play with that rule over there. So that if it was really intuitive, then books on C-star algebras for quantum mechanics would have written this, and they don't. So I'm not sure how intuitive it is.
Oh, okay, sir. Okay, so that's what I asked.
Okay.
Any other question?
I have a question.
Yeah, sure.
Professor Sanders, this is a mathematical question. So suppose I have an operator H, which I know is not self-adjoint in the usual sense of self-adjoint. So is it always guaranteed that I can create an eta, the conjugate eta, such that I can make it adjoint in the sense that you were describing? And if not, what are the conditions on the operator that has to be satisfied in order that I can make it self-adjoint in the sense of, conjugating it with eta?
Okay, so you can see slide 6 now, right?
Yes.
Okay, yeah, those are the rules. So, and this goes back to Bender and Bochert, that it's not always possible. So given an operator H, call it a Hamiltonian, but there's no good reason to call it a Hamiltonian. It is not self-adjoint. Then I think what you're asking is, what are the rules by which we can construct the eta? And it's right here down in most of Azade's proof, which I write in 3 lines, is, and I've restricted here to the finite dimensional case, but it's extendable to infinite dimension. But in he deals with the finite dimensional case, provided that H satisfies, that it commutes with PT, with P linear isometry in Hilbert-space, T the antilinear isometry, and also that the H that you're asking about in PT share all eigenvectors, then there exists that eta.
What I'm saying is this P and T need not be unique, right? I mean, given an H, maybe we can construct a P linear and antilinear isometry such that it commutes, but does it always guarantee that it commutes with all possible P and T that can be?
Well, so the way I've written it here wasn't in literature, and I tried to get it. It was actually hard to discern what comes first. And so in the way I've written it, P and T are given, and then H is PT-symmetric if it satisfies that condition. And I think it's related to your question. In your question is more given H.
Yes. What are the conditions? Yeah. So that we are guaranteed that there exists an eta such that it is self-adjoint in the sense that you've described.
Yeah, and I don't know of any rules that answer the question. I think it's a good question. And the question you're asking went through my mind a lot. How can I formulate this? And so this is formulated in a way that dodges your question. And your question is important. You're saying, given arbitrary H, then you want a test to decide whether it can be put in this form. And I don't know the answer. Probably, I don't know if it's hard to answer, but I don't know what it is.
The reason I ask is because this is reminiscent of Sturm-Liouville theory, where we try to make any given operator into a self-adjoint by changing the inner product. But there, those etas are actually scalars. So I was wondering if and there are a set of rules which has to be satisfied. So I was wondering if there is something similar. Can I ask another question?
Yeah, I'll just comment on that one. I mean, I think it's a good question. I don't know the answer, but if Sturm-Liouville theory gives an insight into it, it's worth putting it down on paper.
Okay, so I have another question. Is it okay if I ask one more question?
It's okay with me.
Sure.
Okay, so can you go to the first slide where you described the usual inner product? Okay, so my question is basically this. So the inner product, we can also think of it as for each, so the inner product with, let's say, bra phi with ket psi. We can interpret phi to be a linear functional that maps vectors in Hilbert space to the underlying field. Right?
Yep, I agree with that.
Yes. So in the new inner product, what happens is that instead of bra phi, we have bra phi multiplied with eta. And I think you have assumed that eta is invertible, or it's a given that eta is invertible. I think eta inverse exists for eta. So intuitively, I feel, I don't know if I'm right. So what is happening is that instead of the linear functional phi, the inner product is defined in such a way that instead of the linear functional that corresponds to the bra phi, there is another phi prime. So we are just actually sort of shifting the linear functionals around. So instead of associating phi with the functional f, we are associating phi with the functional f prime. That is that f prime and f are related by eta. So is that right, or am I missing something?
Yeah, and that's here. You see the change of inner product that I've written. This is what you're talking about. So given ket phi and kep psi, then you're asking about the rule for bra phi. So the change of inner product is plugging in an eta. Now eta is self-adjoint. So if I put the eta on the right of the vertical bar or on the left, you see their equivalent. And so what you're asking is, can we think of that change of inner product as changing the rule for ket phi to go to bra phi? And so what you just said is built into that expression. It's one way to look at it.
No, I was thinking in terms of linear functionals and not exactly in terms of inner products.
Yeah, that one I didn't go through the math, but that comes back to here. So the linear functionals live in S, and B of H would be the density operator, and these would be pure state vectors, if you like. And so what you're asking about here is given by that pullback. So if we go back to here and we think about what's going on with bras and kets, and we do the pullback, but as I said earlier, when I made that red, we didn't find this clear in the literature. Maybe it's there, but we didn't find anything very clear. So the question you're asking about with the linear functionals, we had to introduce a symbol there to make it clear. So I'm not sure how well posed it is. Like, I agree with what you're saying, but I don't think it's in the literature.
Okay, thank you, Professor Sanders.
Any other question? So can I ask you some question?
Yep.
Okay. So this is so the first one is this: your state. You have taken this omega acting on identity is less than equal to 1. I mean, how does it help in your formulation? What happens if you take this is equal to 1?
If we make it equal to 1, then the norms don't change effectively. So by allowing a state to map identity to less than identity, this is what allows us later just to go back to the channel, or the operation, I should say. The idea that change of inner product can be thought of as a quantum operation, then some sort of unitary evolution, and then mapping back, and the mapping back has a change of norm. So basically we're allowing norm decreasing operations without making it an open system. So how does it help? It allows us to say, if the inner product changed, norms are allowed to decrease, and it's not open system.
I see. So the other one is a name question. So you said that yes, one can actually observe by this process tomography what is the change in inner product. I mean, because it's a completely positive map, may not be traced visually. So I mean, so what sort of physical system one can have in mind so that one can try to figure out that yes, there is a different inner product than what we usually have.
Oh, you're asking how to observe it. Is that the question?
Yes.
Yeah, and that's why we did this qutrit protocol here. So the idea there is we're saying, if the inner product were to change, then what would we see on a qubit? And then we simulate it with the qutrit. And what we would observe is okay, let me put it this way. So the change of the inner product can do two things. Like, let's say you take a qubit, you wake up in the morning and your qubit, the 0 and 1 states are orthogonal. But if the inner product changes, the angle changes. So 0 and 1 might not be orthogonal in the evening. So what would you then observe? Well, one of the things you can get is, well, basically if you have 0 and plus, non-orthogonal states, overlap 1 over root 2. And then by the time you go to sleep at night, plus is now orthogonal to 0. That could happen. Then you could clone it. So you could say, in the morning, I'm given 2 states that are not orthogonal, but by evening, they become orthogonal. And then I'm going to clone them in the evening. And then I have my clone when I wake up in the morning. And then what is forced here, this is where that kappa term comes in, is it says, yes, you can do it, but magically along the way, some of them are going to disappear. And that's why it's equivalent to non-deterministic perfect cloning. And then you can ask questions about entanglement and all that kind of stuff. And you say, well, if the inner product changes, I can do some amazing things. And there are papers out there where they play with this kind of thing, and there are claims of amazing things that turned out to be falsified. So your question is answered by saying there's some amazing things that could happen, but there's enough built-in loss by the norm decreasing property that enough of those go missing that you do amazing things, but your norm decreasing saves quantum mechanics.
I see. Okay. Yeah. So, any other question?
Can I ask a quick question?
Yeah, sure.
There is some understanding that this PT-symmetric quantum mechanics is simulatable in balanced gain loss system and in some classical optical systems using Helmholtz analog to Schrodinger equation, etc. Your contention that it constitutes a CP map, do you see any obvious relation to this proof of CP maps to balanced gain loss systems?
Yeah, and I've collaborated with experimentalists on this, so I'm very, very aware of the technique in the lab, and so let me relate it. So I can tell you the typical way that the experiments are done, and it's exactly what you say, gain loss. So the way that it works is we'll do an experiment, but we need to have gain, but the gain has to be noiseless gain. And so in an experiment, typically what we'll do is we'll attenuate at 2 levels. So we'll have a loss, a real loss, and then we'll have another loss, and then we'll just mathematically rescale our norms so that it looks like the lesser loss looks like a gain, a noiseless gain. And so this is the typical way to do it experimentally. It's just 2 different loss mechanisms, and then pretend that you've lost more than you did, so a lesser loss looks like a gain. That's related very much to what I said here, this idea that we have a mapping that over here. So the E eta is a loss term. In an experiment, we'll do, it could be like a polarization change, whatever, some sort of change of angles is how I think about it. And then we counter it by, let's say, a gain term. And then this kappa captures what goes on. It's just a rescaling. So there's a very close relationship between the mathematics here and what you're talking about in the lab for PT symmetry, and the tweak that we do where we rescale the norm is built into that kappa.
Thank you.
Okay. So if there is no more question, so let us thank the speaker for this wonderful talk. Thank you, Barry. Hopefully, we can invite you for a physical talk also sometime in the future.
Well, that'd be nice. And by the way, I'm trying to come back to India, and I was supposed to come back now. I was hoping I might even be able to be there in person, but
that will be great.
my visa was rejected. So I'm trying again to get a visa. But if I manage to get a visa to come, I'll be coming over and I'll let you know.
Sure. Great. Okay. Thank you very much.
Okay. Thanks a lot.